Copy. Hello. Copy.
Yes, sir.
Oh, am I audible?
Yes, sir. Audible.
Okay.
Rasmi.
Yes, sir.
Purba is ready now?
Yes, sir.
Sir, shall we start?
Yes, yes, please.
Okay. Good evening, all. I, Dr. Prabir Kumar Shetty, the co-coordinator of the Atal FDP. Today is the fourth session. So I welcome all the participants, student and faculty members. And I request Purva to introduce today invited speaker, Professor B.K. Mohanty, and our director, Sir Purva.
Very good evening to one and all present over here. I welcome you all to the fourth session of Faculty Development Program by AICTE Training and Learning on Architecture Design Strategy for Signal Processing Algorithms using Approximation Techniques. Today, Professor B.K. Mohanty, SUIIT Burla, Sambalpur, will tell about his research on the topic Approximate Computation Strategy for Energy Efficient Hardware Designs of Signal Processing Algorithms. He received master degree from Sambalpur University in 1989 and PhD degree in the field of VLSI for digital signal processing from Berhampur University, Odisha in 2000. He has 29 years of teaching and research experience in science and engineering field. Recently, he joined Sambalpur University Institute of Information Technology, Sambalpur University as director. Prior to this, he was associated with Mukesh Patel School of Technology Management and Engineering of Narseh Monje Institute of Management Studies as Associate Dean during 2018 to 21. JP University of Engineering and Technology, Guna, Madhya Pradesh during 2003 to 2018, where he has become full professor in 2007. Prior to that, he was associated with Moody Institute of Education Research, Rajasthan during 2000 to 2003, Birla Institute of Technology and Science, Pilani during 2001-2002, and SKCG College, Palakmundi during 1992 to 2001. He visited Nanyang Technology University, Singapore during 2014 to 2015, and Qatar University, Doha, Qatar during 2012 to 2013 for research assignments. He has published more than 100 technical papers in journals for international repute. Currently, he is serving as associate editor for Journal of Circuits, System and Signal Processing. He was the recipient of Sydney R. Parker and MNSS Best Paper Award for the year 2018 by Circuits, System and Signal Processing. Sir, over to you.
Thank you, Apurva, for a nice introduction. I hope I am audible to everyone. Hello.
Yes, audible. Audible, sir.
Okay. Okay. So, let me share my slide. So my slide, visible to everyone.
Yes, sir, it is visual.
Okay. So let me check. And it is running.
Yes, sir. Running.
Okay. Okay. So let me go to the slide. Okay. So good evening
Yes,
to
sir.
everyone for this fourth session, faculty development program. Basically, the core theme is approximate technique for signal processing algorithms. From the session one and session two, the two speakers, particularly they work, they contributed a lot of the, in this area, particularly the signal processing algorithm and architecture design. They spoke about how, what are the signal processing aspects are there and how a architecture going to be designed, right? There are several issues are there, and how what are the basic things somebody has to think about while discussing or deriving a architecture. Basically, there are in a constant environment, particularly resource constraint, timing constraint, energy constraint. There are several issues are there, and some techniques they also discussed. Now, in this session, basically, we'll discuss about the approximate computation, right? So, now before we go about this, uh, let me tell about this. This is a very unconventional approach, approximate, right? Till now, because these are the all we are going to apply for whatever we'll discuss. This is we're going to apply for a circuit, right? So till now we discuss, whenever we'll work, we always design a circuit to get a correct output. Okay, accuracy or correctness of the circuit we always work on. Okay, of course the resource, how to optimize the resource, how to optimize the time, these are all aspects are there, but within that accuracy always matters. So your output should be accurate. Okay, a circuit, otherwise if your accuracy is wrong, there is no meaning of that circuit. But now we are going to discuss very unconventional approach where we are intentionally going to add the error in the circuit, right? So that means we will make inaccuracy, or in you add you make the circuit inaccurate, okay, and error prone to attain certain objective. Now, why this unconventional approach? Because this is something impurity. By we can call it as a we add something which is it is not acceptable. Okay, particularly in the circuit design. Okay, so first of all, why this is required? Because approximate property is a very emerging, and from last you can say 5 to 8 years, or maybe in the last decade, slowly it is started in 2014-15 onwards. Now it is expanded in almost all areas, not only hardware design, it is also moving into the software side, where many of the computing methods they going to approximate, because certain requirement, okay, it is cannot be met by maintaining the accuracy. Okay, so what are those challenges? Let us understand. So before that, what in this 2 hours, what we will going to discuss, basically the need of approximate computation, why we need this unconventional approach, right? What is the necessity of this? Okay, then scope for approximate computation, where is the scope, okay, to apply? That means when you whatever you do, the application, the application must accept that. Okay, so that means the performance or the application performance, it should not be compromised. Okay, so that is the scope for approximate computation, right? Then approximation of so that is the what are the techniques, what are the approximate computation technique, we are going to also discuss. But much about these techniques will apply, because we are also working since 5 years on this area. So during the physical session, so basically we will take up some algorithms, and we apply, and we will going to demonstrate the how the energy power, the challenges, or how the energy power, we able to reduce by not compromising much on the accuracy or marginally compromising on the accuracy. Okay. And then the fifth one, that is the strategy for circuit approximation. Okay, so then approximate computation techniques, then strategy for circuit approximation. Okay, then strategy to design optimize architecture, because you note that we always applied approximation to a accurate design. Okay, so first of all, your the source design, which is supposed to be a accurate one, okay, that one must be optimized. Otherwise, you know you before optimizing, if you apply approximation, then overall what happened, you are compromising some accuracy to get something. Otherwise, without compromising also could be someone can get, okay, that could be achieved. So that's why optimized architecture is always necessary, which is a source for approximation, right? So these are the 5 topics we are going to discuss in these 2 sessions, that is that within the 2 hours. So let us discuss the first one, the need of approximate computation. Why you need that? So before that, there are certain figures you can just look at. These are the, day in day out, every people, not only in the engineering or sciences, the general people, okay, almost in all applications, that is the audio, video, images, okay, these all we are using. Okay, of course there are the several applications related to that, but behind that a lot of processing are going on, okay, where the processor will do in the back end side. So these are the certain things, figures, it is just make out the how much the computation required, particularly audio. Okay, 1 second audio signal, if you want to process simple filtering, or if you do some noise removal, okay, because mp3, the noise, the music systems, okay, they are what, when they change certain frequency, just it will make it will be the to improve certain certain component, so that it will appear to be very sweet. Okay, because person to person a music vary. Okay, a 10-year or a teenager person like certain type of music, or a middle-aged person like another level of music. Okay, or maybe in the elderly or beyond that, those people they like certain things. Even the male and female also, their acceptability is also different. Okay, so depending on that, different components are manipulated, and the the sweetness or acceptability will improve. Okay, so similarly, so 1 second audio, you can see almost a million multiplications are performed per second. 1 million multiplications, right? Image processing, just a image, okay, and that per image almost a billion. Okay, 10 raised to power 8, it is just a fraction of a billion. Okay, billion multiplications are required. Okay, video processing, 1 second video, over a 10 billion multiplications per second. 10 billion multiplication per second. Just imagine how much the computations are behind all these applications, right? And nowadays we are talking about the machine learning algorithms. Okay, and machine learning algorithms, you can just the convolutional neural network, any neural network can take, it is almost, it is 1 trillion multiplication per image. Just a image, you want to extract certain features, because it assumes that machine learning algorithms, they extract a quality features. Okay, so these features, per image, it is almost 1 trillion multiplications. You can see that how much the computational complexity. Now these all these computations, the demands, machine learning algorithms, now it is applied in every, the application is growing. Now in very few, in maybe in a very short period, maybe your machine learning algorithm come into your mobile phone, or maybe a handheld device, and they can do in the behind the a machine learning algorithm, they can process. Okay, so you can see behind that how many computations they're doing. Okay, so these are the rising demand of computational, okay, computation. This is rising. Okay, every, the there is a, the computation is every, it is just in exponential order, it is rising. Okay, then other side, there is another side. Okay, the storage. So you can see, because all these computation are performed by processors, okay, the computing devices. So there is a, there is a study that reveals that demand of modern systems have far exceed the available resources. Okay, that is modern system, they can do all, provide, they're supposed to do all these kind of computations, or they meet the computational requirement. Okay, availability of such type of systems exceeds, okay, that is the, the exceed the available resources. Okay, the demand is more, but that this is not available. Okay, it is expected that amount of information managed by worldwide data centers will grow 50 fold, while the number of processors will increase only 10-fold. So you can see there's a lot of demand of computing devices. Okay, that is the, the demand is, the computation is 50-fold, but the availability of processor is only 10-fold. So that means by providing, high speed processor also, it is not meeting the, requirement. It is in near future, maybe, the semiconductor technology, it is coming down to 10 nano, from 90 nanometer to 10 nanometer. Okay, so the processor speed is, now all the, i7 processor, the hitting, such a high, that is the gigahertz rate. Okay, processing they're providing. Okay, but even though by increasing the processor rate, also they're not able to meet the computational requirement. Okay, so that is the, something we have to look at. So that is the how we can do, how we meet, because application demands. Okay, so rising performance demands will soon outpace the growth of resource budget. Resource means the availability of all these processors. Okay, they're not able to, that is the demand and the supply, that is the supply is going to be very very short. Okay, they're not able to meet the demand. Okay, making provision of resources alone will not solve the computing industry in the near future. So that means, if even though the processor level will be increased, or it may be faster, or whatever maybe we can do, but even it cannot be meet the demand. Okay, that is the amount of computation. Okay, the demand is going on, so we not able to meet that. Okay, so this is the one aspect of the, that is that the lot of demand, computational demand is there, but the processors or availability of the resource is not that much to meet this demand. So this is one issue. Okay, now there is another side. Okay, other side is, and also fascinating us. Okay, rising demand of high performance and energy efficient systems. Okay, now you can look at from last 10 years or 15 years or 20, even 15 years, not too far. You can see the high computing, the algorithms, they're slowly moving to the highly resource devices. Okay, it is coming to sensors. Now sensors are not doing the video processing, image processing, all algorithm the sensor supposed to do. And sensor is highly, their resource constraint. That means their energy is highly constrained. They run by the battery, and, the sensor supposed to be very small, tiny, and the battery size is also to be very small. Okay, so the, resource availability of resource in the sensor is highly constrained, and it is expected that sensor has to perform many of the things. Okay, you can see all these, and all these application in and around, and it is day by day such application is, it is, it is increasing. Smart sensors everywhere. Okay, and I'll tell you what is that mean of sensors and smart sensors. Okay, wireless sensor network, the application of wireless sensor network is widely increasing, everywhere. Wireless visual sensor networks, you can see the traffic management, or your autonomous vehicle, all these, or vehicle tracking, all these things are application of visual sensors. Okay, the cameras, their wireless cameras, they are all are connected, interconnected, like a wireless visual sensor network. The application is growing. There are lot many, the few applications are already, they are all already working, and few are in the very soon. They also come into the, because otherwise, because these type of visual sensors are coming up. Okay, then IoT applications, then neural computing over a wireless sensors. On the neural network is coming to on a sensor. Okay, so that means you can see a sensor is equipped to provide the computation 1 trillion multiplications. You can already, I already projected the amount of computation a sensor supposed to perform, that much of computations. You can see we are loading day by day, we are loading the such a large amount of computation on a small devices, right? So this is the application demands. That means the because everything, everything in this world is, it is developing based on the demand. So this application demands, so people they're working, and very soon the neural network, it will come into the, that is a very small chip that they perform entire the, the neural computing. Okay, so these are the, so you can see smart sensors. What do you mean by smart sensors? Sensor and smart sensors. Okay. So in the, in the textbook, or in the a BTech student can able to easily understand. Okay, a transducer and a simple ADC. Okay, it constitutes a sensor only. Transducer senses signal, and it will convert it into some either, generally we transmit a signal in a digital mode to take some advantage, and then it will send to the some processing centers. Okay, where, or centralized processing center, where the signal will be processed. But smart sensor, now sensor become big nowadays, are very smart. Okay, now the DSP unit. Okay, the DSP unit is coming. Okay, the signal, the signal processing, which is earlier it is done at the somewhere in the, a centralized processing unit. Okay, where, so now we are not sending the, we are not sending the raw signal to there, the now the signal processing coming to the sensor. Okay, so the DSP unit, the basic purpose of the DSP unit is that it will be process the transducer signal and extract the useful information only. Okay, because in a signal there are many informations are not useful depending on the applications. Okay, many information, maybe some features, it only extracts some features, and those features transmitted, okay, over a very, a resource or bandwidth limited channel. Okay, the transmitter transmit that in a wireless channel, and the wireless channel is always resource constraint, a low bandwidth channel, the signal supposed to transmit. Okay, so this is the smart sensor, and all sensors now become smarter. Okay, and they do function like this. Okay. Now the DSP unit, the DSP unit is supposed to do any of this, or maybe one or two: filtering, estimation, data compression, prediction, multiplexing, sample rate conversion, anything it can supposed to do. Okay, so that the required features it can going to extract, and subsequently it is a very low bit, a number of bits will be very few number of bits only to be transmitted, so energy could be saved. Okay, so this is the, this the smart sensor is supposed to do all these things. Okay, then video sensor, that is the, we have an image. Usually we, the image we capture and send to a computer, and the computer is supposed to perform all the calculations or the algorithms always in on a host computer. Okay, and then it will be processed. Okay, but here a video sensor, now the entire video process, the processing algorithm, now it will coming to the near to the sensing device. Now that, the transform coder. Okay, the image sensor, the image sent to the raw image sent to the transform, and the transform, after the transform image, it will encode it, and then only few bits. Okay, few information bit, that means, in the image compression, the image is almost compressed 99 part, only 1% of the information only it will transmitted, so it will transmitted in a compressed form in a very low bandwidth channel. what we are doing in the currently any images, yeah, either we are receiving on the, in a WhatsApp or Facebook or whatever it is, it is always decompressed when the eh, what when the user want to view it. That time the algorithm, when you click, then the decompression algorithm run and the image is decompressed. Otherwise the image is always remain in a compressed form. Any storage media, it will always remain in a compressed form. So that will be transmitted, and in the receiver end also it is received in the compressed form. Then only whenever the user want it, always it will decompress and it will deliver to the user, right? So the transmission, everything, it will be done in a compressed mode. That means a very few bits the information only transmitted. Okay, so these are the a video sensor supposed to do. Okay, now a video sensing network means the connection, a connected network or the network of all these video sensors. We call it the video sensor, that is the wireless video sensor network. Now here one of the application, okay, that is the neural computing. It is coming over the wireless sensor node. Here localization of a, that is a device free localization. That means we want to localize a position of a person. Okay, and nowadays all the devices, their GPS system is there. Okay, so the with the help of the GPS system, the location of the person easily identified. But if you do not have that device, how you can locate? Okay, so that is called the device free localization. Now you can device free, you can see there are several computing nodes are there. Okay, and these computing nodes, what happened, that is the, there is some intercept will be there, and based on that, this intercept, they will be going to locate the person location. Okay, so these are the called the device free localization. So that is the, it will be, there is some neural computing will be performed to find the location of this person. Okay, so these are the all the sensors, the sensors are happen to, that is the some neural computing the sensors are performing. Okay, so these are all supposed to be neurons, right? So these are the, you can see the type of applications are coming up. Okay, where the amount of computations, okay, are involved, and other side, the resource constraint, they're supposed to be highly energy efficient and high performance. Here high performance mean basically they must, perform computation on real time. Okay, so real time is another challenging issue, that is the high performance means, that is, let it be a video is coming. So if the video is coming, okay, the same rate the computation has to be performed, so that the same rate the process videos or images, it has to be sent to the user. So there should not be any delay, right? So that's why they have to perform in a on a real time, right? So that's why it is called the high performance. So all these, based on this, there are, what is the, what we from this all these applications. Okay, or there are not only the application we discussed just now, or there are many other applications are also. What exactly the we observe from these applications? Okay, exact computation or numerical accuracy is not important in all applications. Okay, there are many applications are there. Okay, exact computation is not required, right? There are some, some accuracy, let it be, you have a, for example, whenever we run the MATLAB, or when you do calculate some values, okay, the decimal point is going on, 8 to 9 digits, since it is a floating point. Okay, or if you choose the double precision, okay, the 64 bits are there. Okay, so based on that, there is a several decimal points. So maybe it is not, this is not necessary for you. After first digit or second digit, we always do some rounding and will not note down entire value, right? So similarly, in all applications, they're not required the accuracy, accurate numerical accuracy is not important. If slightly variation will happen, it is okay. It will not affect the applications. We'll discuss some applications. Okay. A small compromise on accuracy reduces the energy consumption and resource saving substantially. Another way, if you compromise, okay, that means if I am calculating the values up to 6 decimal point, okay, and so much I am doing the rounding. So instead of rounding, if I will not calculate, that means since our rounding means we are throwing out those decimal values. So since we are intention to throw out those values, we can do many changes on those values. If I can insert some errors, okay. Since anyway I am going to throw out, okay. So if I insert some errors, then it is also not matter to us, okay. So in that way, in the same sense, we can also think about here a small compromise on the accuracy, some change in the output values, okay. The it reduces, if you allow those changes, then the energy consumption of the design substantially, it will be energy saving is substantially, there is substantial energy could be saved, or there is a substantial energy could be saved. Just for example, in case of k-mean clustering algorithm, okay, the 50 times energy saving 50 time energy saving can be achieved. You can just compromise 5% of the accuracy, okay. In the k-mean clustering, k-mean, just you can find a, the it is just a, the it's not required to find exactly. If the accuracy slightly can vary, so in a 5% variation you can accept, then 50% energy saving could be achieved, okay. This is just an example. So this is just telling us, if we can able to, because since there is a applications are there, okay, lot of computation demand is there, and the available resource is always limited. Now within that we want to run the, we have to meet those computations. Now here what happened, we are compromising on the quality, okay, with a purpose that we can do by compromising certain amount of quality, we can able to meet the required, that is the computational task or everything we can able to meet. So that is the basic objective. So now we'll move to the scope of approximate computation, right? So, first of all, what are those applications we can implement? Because as in the beginning I told you, approximate computation, it is a very unconventional approach. Okay, unconventional approach means we are going to introduce the error. So all applications, they not tolerate error, okay. So which of those applications they tolerate the error? So that means if we can insert some amount of we can compromise on the accuracy, then the application not affect, or the performance of the application not affect so much, okay. So what are those, okay. So error resilience
Sir,
use human brain. Hello, yes.
sir, audio is fluctuating.
Oh, fluctuating.
Yes, sir.
So let me only,
Sir, one thing you do, you just stop your video.
okay.
I think then it may be solved. Otherwise, you joined in another mobile also.
Yeah, yeah, yeah. That could be much better.
Yes, sir.
Okay. The screen is not coming. Hello. Now it is okay. Otherwise, I
Yes, sir.
may join
Yes, sir.
join in.
It's okay. It's
Okay.
okay. Okay, sir.
Now it is
Yes, sir.
okay. Okay, okay.
Yes,
Fine,
sir.
fine. The slide is visible.
Yes, sir. Visual.
Okay. So So let us continue the discussion. So what are those applications? Okay, where we can apply the approximate computation. That means we can compromise the error, that is the accuracy, and it will not affect that is the performance so much. Okay, that means we can able to run the applications without any difficulty, right? So one, that is the error resilience behavior of human brain. Okay. So in a many cases, what happened? The human is the finally the output will be received by the human. Okay, so that is the error receiving behavior of human brain. Okay, so this is particularly the audio whatever will process, finally the recipient is the human. Okay, the finally the audio will be received by the human, right? So whatever it is, will do the changes, that will be only the human able to understand. Okay, or finally the human will tell the changes will be acceptable or not acceptable, everything. Okay, similarly video, the eye will receive, that is the human will receive the video, right? So keeping those, so what is that human, that is called the human perception. Okay, the human perception says that, okay, the human not able to capture small changes. Okay, this is the usual nature of the our human. Okay, the small change, frequent changes we not able to access quickly. For example, you can see that, okay, when a train will run, okay, when it will stand still, you can see the gap between the bogies, and it will start running. You cannot, our eye cannot resolve those gaps, right? Similarly, whenever you will see some images, okay, the small variation on the images our eye not able to capture. You can see, I can show you some images. Okay, the variation in the images, that is the eye not able to capture small variations. Okay, so these are the called the error resilience behavior of the human brain. Okay, small there is small changes, our brain is such that if the small changes happens, then we're not able to capture. Okay, so that is the our brain, it is automatic, the brain automatic, it will feel some missing information, right? That is the same concept applied in the video. In a video, in a motion picture, the video is a sequence of images. Okay, so that is when you can send the images in a particular rate of time. Okay, in a particular rate, then it appear continuous, otherwise the images are discrete. When it will run at a certain rate, our eye not able to capture, and it appears a continuous manner. On the screen you can see everything is continuously moving. Okay, there is no discontinuity is there. So that is, the that is our own, there is a nature of the brain. Okay, that is that it able to feel the missing information. Okay, the because our brain keep some information, it capture and it keep it for few seconds. Even somebody will come in front of us, immediately the person goes out, we still remember the visual appearance of the person. Okay, it is very natural. Okay, then another is not remember rapid changes. If something is happen very quickly, we not able to remember. Okay, so these are the certain things we call, these are the human perception, and that always help us. Okay, to do some changes in the processing. Okay, here is one example, variation in the audio. The audio music is there. Okay, if you look at the audio music, because basically for signal processing, what went the audio music a signal, we collect some samples. So that means all sample values, if you can plot, you will get such type of curves. Okay, now if you change some values in the samples, that means the curve might be some peaks will be slightly changed. But when you play it, then the those small changes, our ear not able to capture those changes, and it appears to be same type of, same music. Then you cannot tell that there is some variation is there, anything. So those variation you cannot able to capture, right? Then here you can see there are two images. Okay, I hope that is the anyone can able to find. Okay, is there any change is there or any difference in two images? I don't think any change is there. Okay, I don't think any changes are there. Okay, so but you can see visual, in terms of visual appearance, both images are identical, but you can see there is a variation, the quality variation. One is generally we images, the quality we represent in terms of, PSNR value. One is 73, another is 68, and these two images are processed by two separate designs. Okay, later on we can discuss in the physical session. These two images are processed by two separate designs. Okay, of different, That is there are different accuracies are there, but in terms of visual quality, you almost see that both are identical, right? So these are the such variations our eye not able to capture, and we take that as an advantage, okay, and we will formulate how to process them. Then here, particularly we call, that is the audio video I call. So those are we call as a multimedia signals. Okay, that is the audio, sound, image, video, computer graphics. These are all called the multimedia signals. Okay. Now we can see the multimedia related applications. Okay, that is the your that is the music, video, or images, or gaming. Okay, these are all there are several such applications are internet related, internet applications that these are currently going on. Okay, and all such applications, that is the we can able to apply. Okay, we can compromise the accuracy while processing those signals related to this application. Then here, then applications are based on the, that is the predictions. There are many applications. Okay, they are based on the predictions, estimations, feature extractions, classifications. Note that these are the predictions, means there is some error is always being there. You cannot predict anything accurately. Okay, you can very closely you can predict, but you cannot predict something accurately. Okay, so that means estimation, it is not exact value you cannot estimate, it is near to that. Okay, so that means in all these applications there is always being some error. Okay, so the output delivered in the presence of error. Similarly, feature extractions, the features, you can these features mostly or the statistical features or something like that. Okay, so those features are slightly the value will vary. Okay, so that's why the when you classify, the accuracy is near to 100%, or we always expect my accuracy is better. Okay, when it is reached the near to 100%, it never reaches the 100%. Okay, now all these application, all these prediction, estimation, these are the some signal processing technique. Based on that, you can see on the right side. Okay, there is this application, that is the machine learning applications. Okay, and they are somehow these machine learning applications are they use for prediction or some estimation or feature extraction or classification. You can see there are a lot of applications are there. Okay, image recognition, speech recognition, traffic prediction. Okay, product recommendations, self-driving cars, email spam and malware filtering. Okay, virtual personal assistant, online fraud detection, stock market trading, medical diagnosis, automatic language translation. There's so many. Okay, many of things might be the as the postgraduate or might be in PhD level, many of the faculty members might be they working on that area. So you can see the applications. Okay, so the basic discussion here is that in all these applications, the there is a some error always present on the output or during the processing. Okay, now here you can see the application, that is the application itself have error resilient. That means if some error will appears, then the application not going to affect it so much. That is called inherent application resilience. Okay, error resilience we can call. Okay, or you can see the input pattern. Okay, noisy input. Okay, whenever the input is noisy, so that means it is always remain as a noisy, there is some variation in the output is always there, right? So that means whenever there is a change in the input, the noise will vary, the output also some amount of vary, or the related application, that within that noise environment, it will, is something the application predict, it is use some prediction something to predicting something, then it will near to that. That is the requirement of the application. Okay, redundant data. Okay, when you have a large number of the images, like so many redundant data. Okay, so in images, whenever there is some changes will going to happen, it will be able to that what those changes can tolerated by the application. Okay, perceptual limitations. That is the we already discussed about the human perceptual limitations. Okay, then statistical and probabilistic computations, computation patterns. Any algorithm based on the statistic of probabilities. Okay, there is no accurate values are there. There is some always variation is always there. Okay, then self-healing, just like the human brain we already discussed. So these are error resilient. Okay, so that means any application is dealing all since kind either type of input or type of output or computation pattern. So that means the error resilient. So that means in those cases we can play with the error. Okay, safely we can play with the error. Okay, so to gain or to gain certain things, because we are intentionally playing or introducing the error to gain something else. Okay, so that means the what we can conclude here, no accurate result is available on all these cases. Accuracy loss by a small amount does not affect much the overall application performance. That overall the we can conclude from here, right? So numerical accuracy is not important. Okay, this is the bottom line. Okay, so that is the numerical accuracy is not important. Okay, we can change the, you can compromise on the numerical accuracy. Then this is very interesting, error and hardware performance trade-off. Now error is, now in all these cases you can see we can we can develop some algorithms, or you can develop some way where error is considered to be a commodity. Okay, so that means you can negotiate the error to gain something. Okay, so that is called the error hardware performance trade-off, right? So error resilient applications allows to introduce a small amount of computational error. Okay, so error resilient because small changes it able to tolerate. So this is just for advantage for us. Okay, so that we can introduce some errors. Okay, so that is a computational errors we can introduce. Computational error result accuracy loss. Obviously when you introduce some computational error, that means when I multiply two numbers, I not exactly my multiplier supposed to perform the exact out result, multiplication result. I can change. Okay, the calculation of the way the multiplication algorithm it is doing, I can change. So maybe the output going to some, it will produce some output with some error. Okay, so that is called the computational error. Maybe adders they cannot they should not be do the accurate addition, they some imperfection we can add. Okay, so these are the called the computational error. So this computational error, obviously it will do some accuracy loss. The output always produce under certain amount of error. Okay, and
Sir,
yes, hello.
sir, total audio is very, very bad quality.
Okay, so let me I'll join in another device, right? Hello.
Yes, sir.
Okay,
Yes, sir.
just a
Yes,
minute.
sir.
Huh?
Hmm. Yes.
Okay, let me, maybe the network will be weak. Okay. Hello. Hello.
Yes, sir.
It is
Yes,
better.
sir. Yes,
Oh,
sir. Better.
okay, okay, okay. Shall we continue?
Yes.
Okay, okay, okay. Sorry for the interruption.
It's okay.
Okay, so 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 we can introduce the computational errors. So the computational error result accuracy loss, right? So a small percentage of accuracy loss does not affect the application performance much. Okay, so that is the because the error resilient behavior of the applications. Okay, so a small percentage error it will not going to affect. Okay, so now the so that we take as a advantage or privilege. Okay, that the accuracy loss can be traded to enhance the hardware efficiency. Hardware efficiency means the resource and energy saving, okay, of the design. So the accuracy loss, whatever the accuracy loss we are introducing with intention that there is a some saving, okay, not some saving, there is a substantial saving, okay, of resource, either resource and energy. Okay, so that is the thumb line of the approximate computations, that is where errors are traded as a commodity to save the resource and energy. Okay, so that is the approach. So all the designs will be in directed in that line, that is the with a small, the how much error you are introducing and how much the saving you are getting. Okay, so that gives the the design efficiency of the approximate that is the computation. So approximate computations set the trade-off between error and hardware performance. Okay, so that means with a conventional approach, design approach, whatever the hardware efficiency you have achieved, okay, then after that if you want further to enhance, because if the through the conventional approach you not able to enhance, because there is always a certain limitation, okay, how much you can the efficiency you can improve, okay, or how much the you can optimize. So beyond that, if you want to optimize the design beyond that, then we can apply the approximate computation, where error we can introduce and we can do some amount of further amount of saving. Okay, so here that is the scope of approximate computation. Okay, what is the scope? Several applications we already discussed. Again, I am recapping here. Several applications use multimedia signals. I already told you multiplayer signals, because human, most of the multiplayer outputs and results is received by the human, and there is a perception, the human perception. Okay, so there is always, there is a scope. Okay, so several applications use multimedia signals. That is always advantageous for us. Machine learning algorithms are increasing use in applications, and the related algorithms are computation intensive. Okay, so machine learning algorithms are they are increasing use, and in all machine learning algorithms I already told you there is some sort of predictions, estimations, okay, classifications, all these things are in. So there is a we not really numerical accuracy is not so much important. Okay, so that's why what happened, and other side they are all computation intensive, lot of computation they involve. So that means they really want some approximate techniques should be applied, so that we can bring those machine learning algorithms into a resource constrained device where the machine learning algorithms can be run, right? So the problem other side is many applications are runs over a sensor nodes constrained by resource. Okay, that is the multimedia signals. Now the sensors are supposed to perform the processing of multimedia signals, and those related algorithms are highly computation intensive. Okay, so that's why what meant that, and these sensor nodes are constrained by resource. So other side you have a resource constraint, one side, other side the huge amount of computation you want to bring it to the sensor node. So that is the approximation. By using the approximate computation, it will enable, okay, it enable the algorithms to be bring into a that is the sensor node which is the resource constraint, and it can run. Such algorithms need to be implemented in dedicated hardware to improve application performance. Okay, so all these are algorithms that are highly computation intensive, and you can't bring them in a resource constraint. There is a demand that you have to bring it, that is the if all those algorithms we can bring it to in a sensor node, then sensors become more smarter, and then you have lot many applications, demands are there, and you can new applications you can also you can up there is a new type of application you can, just like traffic management, okay, surveillance, security, okay. So all these things you can do much better way. So opportunity, okay. So on the circuit design point of view, what are the opportunity available before us? Okay, SNR requirement of applications are widely vary, right? All applications, although we discuss all applications can tolerate the error, okay, how much error they can tolerate. So depending on that, you can estimate the error amount, and you can negotiate or you can trade with the hardware saving. Okay, so that is the error is not important. Output error is not important. Important is SNR. Okay, signal to noise ratio. Okay, so SNR requirement of applications are widely vary. Different applications they have a different SNR requirement. Okay, so it's not necessary that you have to deploy it in if application requiring, let it be, for example, just you want to a application you want to distinguish between, let it be a building, a road, or let it be a garden, or maybe a water reservoir, something like you want to locate. Okay, for all these to distinguish between these two, you not require so much of accuracy. Building and road easily can be identified with a very low resolution image. You can easily identify those. You not require such a high resolution image. You have to develop, send to the user, so that user able to distinguish between which is the road, which is the building, or that is right. So different applications they have a different SNR requirement. Other side is huge demand of power and energy efficient systems for smart applications. Huge demand. Okay, because nowadays power, okay, or energy is the major constraint. Okay, because most of these that is the smart applications, they all run by battery. Okay, the energy budget is very limited, and the way the computing, okay, the computing load, or you can say computational load is increasing, or the processing increasing, but battery, batteries, that energy availability energy or battery energy is not increasing that way. So there is always a demand of energy efficient systems, okay, particularly for smart applications. So limitation of conventional design methods, so I already spoke about. Okay, because the limitation of the conventional design approach, we always go for an unconventional design approach, which is the approximate computation. This is the that is the opportunity. Otherwise, why we have to go for the approximate computation. So finally, the approximate computation could help to overcome the limitation of conventional design methods. Okay, which is the things which is we not able to achieve through a conventional design approach, we could have in an approximate design. So finally, the approximate computation has a huge scope to improve system performance, right? These are the all the targeted applications, not limited, but mainly we can target for smart sensors and IoT applications. Okay, because all these applications, they have the SNR requirement, or they can able to tolerate some amount of error, or the accuracy is not numerical, not important for all these. Okay, so all these applications we can able to compromise some amount of accuracy, and we can improve the performance substantially. Okay, so there is a huge scope. Approximate computation is the emerging technique and widely used in several application areas. Nowadays, approximate computation applied in several areas. Okay, we are in this FDP, we are going to discuss a very limited things. Okay, but it is not limited to only to this. There is several. Okay, if you can Google, You can find there are so many applications or so many hardware, because the hardware design also in different stages are there. Okay, we are only confined to a particular stage, but there is another different other stages are there where approximate computation also could be applied. Okay, you can make the approximation or the system approximation at any point, even in a software also you can do. So how much the time is there? We need a break, Prabir, or we shall continue?
Yes,
Hello,
sir.
we
Yes,
shall
sir.
continue.
Yes,
Continue.
sir. We may take 5 or 10 minutes break.
Okay,
We'll
let
again
us
continue.
5 minute break. Let us 5 minute break. Right?
Yes, sir. Yes.
Okay. After exactly 5 minutes, we again resume.
Okay.
Prabhi, shall we start? Hello.
हाँ सर स्टार्ट कर दिया होगा।
अच्छा. Okay.
हेलो
Hello.
हाँ सर
Shall we
चालू
start?
कर हाँ
Okay.
सर
Okay.
स्टार्ट करेल दो
Okay. Okay. Okay, participant. So let us resume where you left. Now we'll move to the next topic, that is approximate computation techniques. Okay. So how you can do the how we can approximate a design. Okay. What are the techniques are there? Okay. So if you look at maybe in the day session 2 also, this exact design will be discussed. Okay. So the approximate computation could be at the various design layers of software and hardware, okay, of a system. So you can apply the approximation at the software level and the hardware level. But in this session, basically we are discussing about the hardware design. So let us focus on the hardware design flow. Okay. So you can see there is a very simple there is the hardware design. Particularly we are talking about the integrated circuit design, okay, where you have that is the architecture followed by microarchitecture, then logic design, then transistor circuit design, then layout. Okay. So the microarchitecture and logic design, we call it the behavioral design, and the transistor and layout, that is called the physical design. Okay. So basically the architecture, okay, so whenever you will move towards the top, then the flexibility on the design, the design flexibility is much higher. That means at the architecture level you can do much many changes, okay, whereas at the transistor level your changes will be very minimal. Okay. So the flexibility is higher at the top, and when you go down on the design layers, then the flexibility become also very those flexibility will not be there, they are marginal. Okay. The flexibility become very marginal. So architectural, so that is the, if you do some approximation, so basically algorithm approximation, that is the, you have to do the approximation at the algorithm level, because the from the algorithm architecture is derived directly. Okay. So any changes you do the algorithm level, that will be reflected in the architecture, the changes will be reflected in the architecture. So that is basically at the architecture level. If you want to approximate, then you have to target the algorithm. Basically you have to approximate the algorithm. Then the macro architecture and the logic design, that is we call it the circuit level approximation. Okay. So at the circuit level, that means some Boolean expressions you can do, okay, some changes in the Boolean expression, so then there is some changes will be reflected, okay, in the microarchitecture or the logic design, right. Then that is the transistor level, the device level approximation. So if you do some device level approximation, then your transistor level changes will be reflected, accordingly your design will be approximated. So these are the different layers of approximation, okay, you can apply at any layers to make the changes or to make your design to approximate your design, right. So we now your focus, okay. So because circuit level, as I already discussed you, okay, that is the circuit level, there is a much flexibility is there, okay, related to the transistor level, okay. So we will discuss basically in this particular in the FDP, okay, or in this session, the circuit level approximation we are basically more focusing, okay. So in the when you focus on the circuit level approximation, basically we will focus on the approximation of adders and multipliers, because adders, adders or multipliers are the main building block of the circuit level, okay, because they do the all the calculations, Okay, they related, they you manipulate the numbers using the adders and multipliers. Okay, so that's why the role of the adders and multipliers, that is significant. Okay, so we'll do the approximation in the adders and multipliers, not on the memory side. Memory, what happened, it will only store the data. We are not approximating any memory. Of course, you can approximate the memory also, but we are not doing any approximation to the memory. Okay. So among these adders and multipliers, as you know that multiplier is more complex than the adders. Okay, so most of the works, if you refer the technical literature, there is several works or research, okay, or solutions or designs, approximate design, they suggested basically for the multiplier design. Okay, because it multiply is the more complex. So popular methods are, when you do for the approximation, then the popular methods are logic approximation, bit truncation, and algorithms is the approximation. Okay, so there are 3 level of approximations that is the you can apply. Okay, so in this hierarchy, okay, the error, that is the accuracy loss is very minimal in the logic level approximation, while in the algorithm level approximation the accuracy loss is higher. In the other side, the saving, energy saving or resource saving, or hardware efficiency gain, okay, then algorithm level it is much higher than the logic approximation, reverse one. Logic approximation of Boolean expression or truth table. Basically, intentionally we change the truth table, okay, to add some errors. So that is called the logic approximation. Bit truncation, removal, when you have a string of bits, because you always process particularly we call the word, okay, a group of bits, okay, then you can leave certain if you want to manipulate the numbers, okay, sometime we throw out certain bits. Okay, so that is called the truncation or rounding. Okay, removal of lower order bits from the design. So from the design we throw, okay, you cannot carry all the bits, somewhere you have to throw them. Okay, so that is called the bit truncation. So that is one sort of approximation also. How many bits you want to throw? Okay, maybe my output is 16 bit, I can only carry 12 bits, I can throw 4 bits, or you can carry 14 bits, you can throw 2 bits. Okay, more bit you carry, more resources you have to provide. That means the bits you have to manipulate, so you have to provide more resources. The algorithmic approximation, that is the modification of algebraic formulation. Okay, all this is called the algorithmic approximation. Okay, that is later on when you map it into an architecture, okay, those changes will appear. Now if you talk about the approximation of adder, if I want to, because initially we started with, okay, that is the logic circuit level approximation, where we are targeting approximating a adder and a multiplier. Okay, so when somebody want to do approximation a adder, what are the techniques somebody has to apply, or generally apply means that is basically in the literature what are the technique people they usually apply. Okay, full adder. Okay, so logic approximation, basically full adder truth table people they manipulate, okay, so that the number of transistors required with the full adder it might be less, okay, and the delay of the full adder it could be lower. Okay, so basically logic approximation applied to the full adder. Compressor basically multiple bits when you add, okay, that we call the compressor. Okay, that is also logic approximation. Full adder it is also a compressor, that is called 3 to 3 bit added and output is sum and carry, so that is called 3 to 2 compressor. Okay, similarly we have a 4 to 2, 5 to 2, 5 to 4, different compressors are available. Okay, they are applied, logic approximation usually applied. Adder tree, that means that is the multi operand adders, that means multiple values you are going to add together. Okay, let it be I have a 10 values or 8 values, I want to add those 8 values, okay, I want to accumulate those 8 values together at a time. So that is called the adder tree. Okay. Similarly, shift adder tree, that is, in the multiplication table, you can see all the partial product, they always appear appended in a shifted form, and you have to add together. That is called the shift adder tree. Okay. So these are the all, that is the two way. If you want to approximate these two, the usual technique is either logic approximation or bit truncation. Okay, these two are applied. Then come to the multiplier. We classify the multiplier. Generally, multipliers are classified into two types. One is called logarithmic, another non-logarithmic. Okay. So logarithmic, by logarithm method also you can multiply two values, because here what happened, because particularly in hardware, when you do the multiplication in a hardware, okay, we always want to reduce the resource. So when you convert two operand into logarithm domain, okay, then what happened, after converting to logarithm domain, you have to just simply do the addition, because the multiplication is supposed to be addition in the logarithm domain. So a single addition is required in the logarithm domain, and then after that addition, again you apply the anti-log and recover the value, convert the value in the decimal form. Okay, so that is called the logarithmic multiplier. And another is the non-logarithmic multiplier, which is normally the Booth multiplier or Pauli multiplier. These are all sign multiplication they perform. So these are all very popular. Okay, so in the logarithm multiplier, if you see the building block, okay, here x and y are the two operands. You want to multiply them, the result is z. So what you will do, the x and y, they converted through a logarithm converter. So you will get the log, okay, with some base, might be base 10 or maybe base 2, it depends. Okay, you get some, that is logarithm domain, get the x and y, and then just simply you add them, the result you convert it to anti-log, and you will get the product. Okay, so that means two, the converter and a single adder. So that is called the logarithmic multiplier. The non-logarithmic, this is generally Booth multiplier or Pauli multiplier. Generally one x and y, one you can use to generate all the partial product. Okay, partial product encoder, then those partial product are selected, that is for a particular operand. Okay, y, okay, depending on the bit pattern, you have to select the partial product, and those selected partial product basically added. Okay, that is the in a shift adder tree, so that you will get the output, okay, product. So these are the, these are the building blocks basically. So you can apply the approximation any of these building blocks. Okay, in a logarithm multiplier, you can approximate the logarithm converter or anti-log converter or the adder. Okay, in case of non-logarithm multiplier, you can approximate the partial product encoder or the partial product selector or adder unit. Either all of three you can approximate, or maybe one of them you can approximate, or more than one you can approximate. There are all possibilities are available, because when you want to intend to enter the error, so error you can easily enter by changing anything. You can error, you can okay, so that you can do. All those changes are a possibility are there. So in a logarithm multiplier, I already told you, okay, there are three building blocks: logarithm converter, adder, anti-log converter, because all these are generally the logic approximation is usually applied. Okay. Non-logarithm multiplier, partial product encoder, you can apply logic approximation or you can apply algorithmic approximation, because algorithm approximation what means, the number of partial product you can change the algorithm, and might be the encoder algorithm you can change. There is a number of partial product also you can change. Okay, we'll discuss in the physical session some of the examples, okay, related to this. Then partial product selector, that is the logic approximation you can apply. Then shift adder tree, logic approximation, truncation, both you can apply, or maybe one of them you can apply to make them approximate. So these are the some, that is the techniques. Okay, in the literature people they do apply, or they already applied on that. Okay, there are several works are there, If somebody is interested, they can visit the literature, they can find. Then strategy for circuit approximation. So if somebody want to work in the approximate computing, okay, or want to do some circuit approximation, what should be the strategy? Because it is not so easy. The way I spoke about here, okay, it is not so easy. So what should be the strategy? What is the way out? Okay, how someone would plan, okay, to do the work? So that here I am just throwing, okay, from whatever we gain from the last 5 years of research, that I am putting it here. Okay. So design approximation, okay, the key aspects. What are the key aspects? Okay. So whatever you have the algorithm, because any algorithm you want to finally, if a multiplication or adder or maybe anything, any signal processing algorithm, let it be DCT, okay, or maybe a filtering, a filter design circuit I want to approximate. Okay, finally it comprises some adders, multipliers. Okay, anyway, I approximate them. Okay, so how we can, how we can check the quality of your approximation, because the quality is important. That means how much error you introduce, how you can measure the error, okay, and how much the gain you have, because you are trading the error for performance gain. Okay, that trade-off should be set. Okay, so one way is that the approximation of the computation, you have to whatever the algorithm you approximate the, that is the computations, that is you have to introduce the computational error. Okay, then after introducing the computational error, then you have to measure, that is called the precise error simulation. You have to measure the error very precisely. If your simulation is going to wrong, then might be because of your wrong simulation, otherwise the algorithm not having that much of error, then your approximation will be not be properly verified, or it is not properly checked. Okay, so that your result will not going to be correlate. Okay, so that is the precise error simulation, that is the key concept. Okay, then other side is, once you have an algorithm, you have to map into an architecture. First, whatever the algorithm, either DCT or FR, whatever I told you, okay, the targeted algorithm, you have to map it into, or a multiplier algorithm, you have to map it into architecture. Okay, then in that architecture, you have to apply the approximation. Okay, and then precise hardware simulation to measure how much the energy gain, okay, energy reduction, or how much the resource consumption. Okay, so all those, that is the resource saving, everything you have to precisely measure. Then only you can set the error versus the hardware performance. Okay, you can study and you can tell about the how good your approximation. So error metric, basically these are the generally performing parameters: average error distance, okay, maximum error distance, average relative error, average accuracy, okay, mean square error, signal to noise ratio, peak signal to noise ratio. So these are some performing metrics. Okay, it depends because if you are dealing with the image processing algorithm, then you have to measure finally the effect, the accuracy effect of your error in terms of peak signal to noise ratio, how much the signal to noise ratio reduced. Okay, so that you have to measure. Or maybe it is not a image processing, maybe a audio or one dimensional signal processing, anything, or filtering, something like that. The signal to noise ratio, or it a communication algorithm. Okay, signal to noise ratio you can measure in terms of bit error rate or something like that. Okay, then all these to measure signal to noise ratio, peak signal to noise ratio, you have to find the mean square error. Okay, so all these are measuring parameters. You have to find some way, or you have to find some way to find this error metric. Okay, to measure this parameters. Okay, then hardware performance metric, basically we talk about the critical path delay. Okay, so that will set the how much the maximum clocking speed of your design. Okay, then area means this is basically called the silicon cost. okay, power consumption. Then all these three, that is the area delay product, okay, that parameter basically it measure the resource consumption and the throughput rate, that means the performance, okay. So whenever you have a higher performance, you have to provide some resource. So it always, you know, you have to find a common parameter, because if your different designs are there, okay, and they provide different performances, how we can measure in a common platform, okay, or in a normalized form, how you can measure. So that is the area delay product is a normalized form where, okay, the resource and performance or throughput rate they measure together, okay. Similarly, computation time, okay. So the computation time, maybe your a given task will be completed in a several clock cycles. So you have to measure the total amount of time taken by your system to complete the task. That is called the computation time, okay. Then energy consumption of your design. So these are all performing parameters are there, which will be measure the hardware performance metric. Now basically, you know, we'll talk about, okay, when you about the hardware design, we talk about the precision, okay. So that is the fixed point versus floating point, okay. So we all know that floating point, whenever we will do we all the processors, you know, general purpose computers, whatever it is, that is the all the calculations are done through the floating point, okay. So your calculation you can be done through the floating point or through the fixed point, okay, arithmetic. So there are some advantages, some disadvantages, okay. So whenever we will design something, either we will choose the fixed point or floating point, depends. So floating point operations, okay, the bit width or the signal width is very large, okay, single precision 32 bit, okay, double precision 64 bit, long double 80 bits, okay. So these are the bit precisions the floating point they offers, and floating point generally it is used in the general purpose processor, okay. So in a desktop computer or in a MATLAB, whatever value you calculate, these are all floating point values, right. So floating point generally used for representing very small and very large numbers. Whenever we are dealing with very small numbers and decimal point, let it be 9, 10, okay, or very large numbers, then only floating point is used. Otherwise, use of floating point, it is a, you know, wastage of resource basically, because even though your values are very small or is a, you know, in variation not that much, it always for every value it will use, let it be single precision 32 bit it going to provide, okay. So that is the advantage. That is the in the floating point, when you add two numbers, the width, okay, or the word length not going to change. That means all the values, okay, 32 is a single precision, that is 32 bit, 32 bit you add, then your result also within the 32 bit, okay. So that means there is no growth in the word size, okay, word length size, there is no variation in the word length size in the floating point. That is one advantage, okay. All the values are adjusted in a given precision, okay. So that is the advantage of floating point. So you should not bother about the word length, okay. There is a change in the word length, there is never word length never change, okay. Either you 100 multiplication you perform or 1 million multiplication you perform, whatever number of multiplication you perform, your result always accommodated within that given precision. Disadvantage, processor is more complex and consume a large amount, because you know bus width, okay. So your bus width will going to be 32 bit, okay, or so that's why what happened, or multiple bytes are used, okay. So the processor become more complex, okay. Or if you use the floating point, the processor going to be more complex and it consume large amount of power also. So generally, if it is not required that general purpose type, okay, because general purpose in all variety of work you can task you can assign, then generally floating point processing or floating point calculations precision is never preferred. Then fixed point, in a fixed point in the normally binary method, okay. So that is the word length is assigned according to the sample value. So if my value is, let it be 10, okay, decimal value 10, then accordingly I can assign the required number of bits. 4 bit is enough to represent 10. If my value is 100, accordingly I can represent, let it be 7 bits, I can, it is enough for to represent 100, Okay, so like that, depending on the sample value, you can allocate the bits. That is called the fixed point of representation. Commonly used in embedded processors or dedicated processors constrained by the resource. All the microprocessors, they are 8-bit. That means the width is fixed 8, okay, or 16-bit or 32-bit, okay. So that is that they all are fixed point, right? So fixed point operations, that is the one problem actually. Fixed point operations, word length size increases after every arithmetic operation. Unlike the floating point, in fixed point, word length grows. Okay, so that means you can see in case of addition, if you add two numbers of size w, okay, then your output is w plus 1. If you not provide a 1 bit extra to at the output, your output going to be, okay, overflow. That means the value cannot be accommodated within that bits. So that means more higher number of bits you can assign, okay, that is one extra bit you can assign after every addition. Similarly, in case of multiplication, okay, when two, that is the two operands of size w, you can multiply, then the result is accommodated within required, it required to deliver the correct output, it required 2w, that is the width. That means 8-bit to multiply, your result required 16-bit, or 16-bit multiply, your result will be 32-bit. That is the one problem, that is the doubles after every multiplication. The size will be bit width or the word length size, it always doubles after multiplication. This is one major issue. You can see here, it is a very common, it is just I took a example, but such type of calculations in a signal processing, many such calculations, multiplication perform back to back, multiplication, additions, they perform back to back. Okay, so you can see at the output, at the end of the, at the input, all operands are w bit size, but at the output, what's with the bit width in a fixed point. Okay, so when w bit we add, we can give w plus 1. Okay, when w plus 1 and w is multiplied, we get 2w plus 1. Similarly, again, when you add, you get 2w plus 2. Okay, then this is 2w plus 3. Okay, then here 2w plus 3, then multiply w, it is 3w plus 3. Like that you can go, okay, calculating this, it is very simple. Okay, so you will get at the output, your word length should be 4w plus 5. This should be the minimum word length to get the correct accurate value. If you not provide this much of bit size, okay, your output going to be wrong. Okay, for example, if you consider that for w is equal to 16, if my 16-bit all the operands or inputs are 16-bit size, then your output word length is 69. Okay, for 20-bit operand or sample value, your output is 85. You can see this is increasing, it is more than your floating point size. Okay, and in a signal processing, there are, this is just a very small calculation, but such type of back to back, there are hundreds of multiplication are performed. So that means your word length size is growing infinitely. That is a major issue. Okay, the problem. Several multiplication and additions are performed on an input operand to calculate an output. Okay, word length size grow is a major issue in a fixed point implementation. Okay, to avoid infinite word length growth, fixed width designs are considered. Fixed width, that means we not allow the word length growth, we have to fix it somewhere. Okay, so that means some error is automatically introduced. Okay, so fixed width designs are only possibility. So input output, so fixed width design. Okay, so in a fixed width design, basically the definition is the input output operand bit width are identical. So if the input output operands are identical, we call it the fixed width. Okay, so here w and w are, when they added, you get the w output. You might be thinking about that, then my value is not correct. Yes, your value is never correct. Okay, so that means now you want to leave one bit. So which one? Generally the lower order bit we want to leave it.
that means LSB we want to leave and the remaining we carry forward. Okay, so that means some error, that is called rounding or truncation error. So some error is always introduced in fixed width calculation. Okay, similarly multiplication, you can see W bit you multiply, your output supposed to be 2W, but from the 2W output, okay, you only carry only W bits. That means higher order W bits you can only carry, the lower order W bits you have to leave it. Okay, you have to truncate. Okay, so that means all these calculations they already have some error. Okay, so one LSB of adder output is truncated to obtain the fixed width output. W number of lower bits are calculated full width out, that we already discussed. Okay, now the point is here. Okay, that's in summary. So fixed width design introduced computational error. Okay, because we cannot allow there is an infinite growth of that with the bits. We have to somewhere you have to truncate. So whenever we truncate, then always computation error introduced. Computational error is not important, as I already told you. Computational error is not important, but SNR, output SNR is important. So in this kind of truncation, how much output error basically, okay, introduce, that is important. Okay, so SNR PSNR requirement are widely vary in application, already I told you earlier. Okay, so that means here the truncation model, how you can truncate, where how many bits you have to truncate, that you have to decide. The designer have to design it. Okay, think about it accurately. Okay, so intermediate and output signal width of a specific design to be fixed based on the SNR PSNR requirement of target application. Okay, so how much the SNR PSNR requirement are there, depending on that you can fix the width of the the bit width. Okay, all the intermediate signals or output signals accordingly, so that required SNR can be met, it should not be violated. Let my application require 50 dB of SNR PSNR. So for achieving 50 dB, I can change in between the bit weight accordingly. I can change, I can look at my output is meeting that 50 dB or not. If it is not meeting, I can provide more bit in the design, or if it is meeting, okay, if it is more than that, I can reduce somewhere. Okay, so how to study this, your target SNR, truncation, all these things, how someone will be able to manage it. Somebody cannot calculate on a pen and paper. Okay, because millions and millions bits you have to process, you cannot keep track, all the values you cannot calculate. So you have to engage a system and you have to monitor it. So that is called the simulation model. That is called the simulation model. Okay, how someone that is the design this simulation. Hello, am I audible?
Yes, sir, audible.
Okay, so the simulation model that I already spoke about, you have a two, there are two parts of the approximate design approximation. One is, error metric, estimation of error metric. Another is estimation of hardware performance metric. Okay, so simulation platform one can choose. Okay, for error metric, we are discussing the error metric. One can choose MATLAB or Python. Many people they use the Python. Okay, many of them use the MATLAB. We use the MATLAB. Okay, so whatever you have a target algorithm. Okay, so that algorithm, okay, you have to, first one is you do the floating point simulation. Okay, so that means you have to write the algorithm. Okay, all the input patterns you can give and get the output. Floating point simulation you can perform. That means you write a simple MATLAB code, so that give you the output, because MATLAB code it use the that is all the values are floating point, so you can get the floating point output. Then the same algorithm you can apply to a fixed point simulation. For fixed point simulation you write a separate code. Okay, so you can apply the particular type of either 2's complement arithmetic or whatever integer arithmetic, whatever is possible, you can see it is convenient for you. Okay, so you can do the fixed point simulation. That means all the bits Okay, the input intermediate I can fix it 12 bit, 16 bit, 18 bits, wherever how much it is required. Okay, so based on that you have to select, initially you have to select and do some fixed point simulation, okay, and calculate the output. Okay, so that that floating point simulation and fixed point simulation, these two results you can compare, that is, and based on that you can do the data path optimization. The data path optimization means in a fixed point simulation, okay, how much your data path, okay, width, it is 12 bit is enough to target to receive the target SNR or PSNR, or it is 14 bit is enough, or it is 16 bit enough, what is that? Okay, so you cannot do it, you cannot achieve it in a one iteration, you can do it in multiple iteration, so that you can optimize the data path. Okay, so that your reference design is a floating point, and your fixed point, you can be in the fixed point always some error is there, so that with that error you can find out your PSNR or SNR and just find it. Okay, then once you fix, that is the all your fixed point design is identified, that means all the bit width are identified. Okay, then next is the fixed point simulation using the approximate component. Now in your fixed point simulation you have used the accurate adders, accurate multipliers, all those components are accurate, only you did the bit truncation. Okay, now here the third level is the same fixed point simulation, now you make your adder and multiplications are inaccurate. Okay, maybe multiplier you can make inaccurate, adder may be accurate, or maybe you can do adder inaccurate, multiplier may be accurate, whatever you can way you can think your approach you can do. Okay, so approximate computation component you can introduce, and then you find out the error metric. Now for your error metric, your reference design is the fixed point simulated design. Okay, those values and the approximated the result values you can just compare and find out the error metric. Because your fixed point simulation, it is basically the design which is your conventional approach. Generally in the conventional approach, whatever the design we get, that is the fixed point design. Okay, and that one the reference design, and in the approximate design, which is the non-conventional approach, so whatever the changes we meet, that with reference to that we find measure all the parameters of the error metric. Okay, and this has to be done very precisely, otherwise your result will be going to, you not able to track where or how much the error it is popping up into a design. If you're not able to track, then you cannot able to control your approximation. Then hardware performance metric, generally RTL simulation. Okay, whatever your algorithm, you have to make it do the source coding. Okay, that is generally either you can use the VHDL or Verilog, whatever you like, you can apply RTL simulation, that is the behavioral modeling. Then design synthesis, you can take those source coding source files into some synthesis tools. Okay, maybe Synopsys or Cadence, anything you can apply. Okay, and get all the synthesis result. Okay, so for hardware simulation, this is the pattern you have to follow. Okay, that is a selection of optimized hardware design. I already told you. Okay, that is your target. Okay, for approximation. Okay, for design approximation, your source design is the optimized hardware design. Okay, that should be the source. Okay, that hardware design, okay, you can use, okay, the fixed width component you can apply. Okay, you can apply the fixed width component and then do the HDL coding. Okay, and then do the design synthesis and find out the hardware estimates. Then same the optimized hardware design, now those component are you replace with the approximate component. Okay, this is the there is something wrong is there. Okay, these are the with fixed width component, that is the approximate component. This is the approximate component, right? This is the approximate component. So hardware design with approximate component and do the HDL coding and do the design synthesis. Okay, the hardware estimate. Then you have to compare these two and get all the hardware metric. Okay, area, delay, power, area, delay, product, energy, whatever it is you can find. So this should be the flow. Then performance study. So now you can do the performance study. Accuracy you can take it from the error metric. You can pick up from the error metric and plot against the area, how much the in a hardware design, how much the area. So accuracy versus the area, how it is varying. Accuracy versus the delay, okay, because delay saving, critical path saving, okay, because delay always, whenever your delay will be reduced, there is a your speed will be enhanced, okay. So your computation going to be faster, okay. So that means the accuracy versus delay, how much the delay reduced. Accuracy versus power consumption, accuracy versus area delay product, accuracy versus energy power delay, okay. These are the all you can just do the all this scatter plot, okay. For example, let it be I shown here, okay, scatter plot, okay. Accuracy versus the energy consumption or area delay product, you can see different designs, they showing some type of plot, okay. So here you can see what we are expecting, because all these are some are approximate designs. So what we are expecting, higher accuracy and the lower energy consumption, okay. The design having the lower energy consumption, but accuracy wise it will be higher, okay. So that you can see in the scatter plot, okay. Anything is coming, the design on the right and lowest point, okay, that design, there is some mistake is there, design on the right and lowest point, okay. So is the most efficient approximate design, okay. So that is the rightmost lowest design is the most accurate. So in that way you can just see how your all the, this is just a visual, okay. Through the visual you can able to find out which of your design is giving the best performance or the approximation, best approximation, okay. That means the there is a the accuracy loss is minimum or the lesser accuracy loss, okay, but higher amount of energy gain, okay. That is the energy saving or power saving or area delay product saving, okay. So that give you the better kind of approximation. Well, now we are reaching to the last that is the point of the our content, the strategy for hardware optimized architecture design, okay. If you go back, I am just keep emphasizing all the time, okay. So that is where it is, okay, somewhere we miss, anyway. So you can see here basically, okay, here you can see the selection of hardware optimized hardware design. So maybe in the literature that could be there or it may not be there, might be, all designs are not optimized, okay. So if it is not there, then it is your job before applying the approximation to any of the design, you just see that if the design is not optimized, okay, then you have to optimize the design first, then you must apply the approximation. You should not jump, okay, to apply the approximation directly. So that is the basic requirement, okay. So design, a optimized design must be, you must have a optimized at the you must have a optimized design. So how if it is not there, if a hardware optimized hardware design is if it not available, or you are intended to optimize a hardware design, what are the steps somebody has to follow, okay. What are the steps somebody has to follow? So you can see a hardware design, okay, a hardware design, this is just a basic building block of a hardware design. It has a, because it is particularly we are talking about the hardware accelerator, okay, where it has a logic unit, it has a some on chip memory and a control logic, okay, and the logic unit and it is interacting with the off chip memory, okay. So some off chip, on chip memory, arithmetic unit and a logic controller which will control the operation of the arithmetic unit and memory, addressing everything it will control, okay. So the objective here, because the core, okay, because the on chip memory the off chip memory, okay, the remaining part we call as a core, and the core is interacting the off chip, okay. So the objective is the core has to be, design objective is the area delay power optimization of the core. We want to optimize the core. Okay, the optimized design, hardware optimized design means the area, delay and power, the core has to be area, delay and power optimized. Okay, so that is the hardware optimized design. So you have to optimize. Now since you have a arithmetic logic unit, you have a off-chip memory, okay, control logic, you must understand area, okay, it is the silicon area, okay, but delay, arithmetic unit, different comma adder, multiplier, they have a different amount of delay, okay, memory, okay, memory accessing, it has a different amount of delay, okay, then power consumption, that is the arithmetic unit, they use the logic, combinational logic gates, where the memory, they are read write and static power, dynamic power, the different amount of power consumption is there. So all these taking into account the power consumption. Okay, so basically before somebody has to plan or you have to think about a design, the first and foremost one must has to know the complexity of the algorithm. Okay, or complexity, if that exact that algorithm somebody has to put it in the hardware, okay, how much it is complex, the hardware complex means how many arithmetic unit means it is how many multipliers it is consuming, okay, or how much the memory on chip memory size, how much it is want, okay, all these things somebody has to analyze first. Okay, so it is in general what from our research, because from last 15 years 20 years we are doing research, okay, and in our research many of the papers also we discuss this, okay, that is the one dimensional signal processing systems, that is particularly the filtering, okay, all these are these are all one dimensional signal, okay, processing. In case of one dimensional signal processing algorithms, okay, the memory is only 35% generally the algorithm, okay, when you design a hardware design, okay, hardware, then the memory domain, the resource consumption is only 35%, while 60% is the arithmetic logic unit, okay, 5% is control. So this is the entire distribution of the resource. So that means we can call arithmetic unit is a major component, okay, or major consuming resource component. Then if we move to the 2D signal processing systems, particularly 2D DCT, that is if you are designing a system to process an image or 2D filtering, okay, then the scenario is changing dramatically. Okay, memory is now 85%, okay, and arithmetic is only 14%, and 1% is control. So that means the major resource consuming, okay, component is the memory, it is not the arithmetic unit. Okay, then if you move little bit ahead, that is the for a 3D, that means a video, if you designing a system to process some videos, if a hardware that a video card, okay, a video card basically what happened, it will encode the video, okay, so basically if a video, then you can see the memory is almost 95%, almost memory is entirely dominating, compared to memory, okay, the resource, the arithmetic is almost negligible, you can say. So that is the major power consumption is due to the memory, it is not due to the arithmetic, okay. So that means from this actually from here you can able to find out which of that block is more power consuming or resource consuming, because if you identify that block, then you can optimize, you try to optimize that block on a priority basis, okay, rather than, because if you, for example, if I am planning to a image processing system, a design, okay, for processing an image where the memory is 85%, if I focus to optimize my arithmetic unit, then my gain is not that much, okay, I may optimize, but that not going to result, okay, the whatever the resulted hardware design, then that gain in the the energy saving or area saving, whatever we are targeting, not that much, because we left a component which is 85% resource consuming, we not optimize that, we never did anything to that, but we focus a component which is just 14%. So that, in that way you can think about which is that component you have to first optimize. Okay, you have to pair, because because arithmetic, memory, optimization, they are two separate. Sometimes you try to optimize a memory, your arithmetic unit not become, it will become some overhead will be, you have to add in the arithmetic unit. Overhead means extra, okay, extra penalty you have to add. Sometimes arithmetic unit you optimize, you have to add penalty on the memory, okay, because they not like they're separate unit, you cannot separate them, you cannot separate them, okay. So that's why somebody has to plan how to go about apply that optimization, okay. Anyway, because this is just I'm thinking over, I'm just telling you that is the how somebody will plan about that, okay. Then if you think that if memory is my primary component, major component, I want to optimize my memory, what should be somebody's strategy? If somebody want to optimize the arithmetic unit, okay, then what should be the strategy? Okay, because they have different component, okay, and the strategy should be different, right? So you can see memory, particularly memory domain power consumption is the major problem in all the image and video processing algorithms. Memory is the major problem, okay. For an image processing algorithm, the memory size is somewhere is 1 MB megabyte. Video processing, the memory size is almost more than this, but I am just as a typical value I written 125 MB, okay. So energy consumption due to memory read write only, because normally what when memory power will discuss in the next slide. Memory power, one is because of the static power, okay, because the memory has consumed some resource, that's why it has some static power. And then memory read write, that is called dynamic, okay. So memory read write is a major problem than the static, okay. So energy consumption due to memory read write, okay. Data shows that 1 bit memory read write, it will consume 1 nanojoule. This is the data, okay. 1 read write memory per bit, it 1 nanojoule, okay. If you assume, okay, the whatever the memory size is given for image processing 1 MB, let you have a 1 MB of memory in your design, and whatever the data is there, you just reading one time only, because normally whatever the value in the memory, many times it read, okay, we read the many times during the algorithm run, okay. But if you assume let it be, okay, only each value will read only one time, okay. So you can see 1 millijoule energy consumption, okay, for memory operations, that is the for 1 million memory operations, that is the energy consumption in 1 millijoule, okay. For 1 MB, if you want to read only all each value, you can read one time only, okay, then 1 millijoule of energy consumption, 125 millijoule, okay. Note that your entire chip, okay, your arithmetic or entire chip, 1 millijoule or 125 millijoule is too much, okay. Nowadays integrated circuits, hardware accelerator, the energy consumption is normally 100 to 200 millijoule, okay, or even nanojoule, nanojoule also, microjoule it is going, it is even not in the millijoule. But you can see the memory power consumption is major problem, okay. So here memory, if somebody want to reduce memory optimization, somebody has to do, okay, what are the steps somebody has to one has to take, okay. So anyway, so memory these are all we can call, okay. So this we are skipping because memory hmm? Hello.
Sir, next 10 to 15 minutes wind up, sir, please.
Sir, it is not audible.
Okay. Audible? Hello?
Yes, sir.
Yes, sir, it is audible now.
Okay, sorry. So memory optimization, memory saving, that means you can save the memory bits. Memory reuse, read the memory values from the memory and reuse it wherever you want, rather than sending back to the memory. Okay, or memory sharing, that means a one block of memory you can share it multiple operations. Okay, or memory bandwidth saving. Memory bandwidth means number of read write memory per output, that is called the memory bandwidth. So to calculate one output, how many times you are reading the memory, how many memory operations you are performing, that is called the memory bandwidth saving. Okay, so on this order, top one, if you do the first one, design, maximum saving you have, then later on move on the down, that is the your amount of saving accordingly reduce. Okay, but always any of this you can do, there is always guaranteed that you have a some power saving and energy saving. So saving in terms of area and power. Anyway, let us move. Arithmetic complexity, you want to optimize your adder or multiplier. Okay, so what are the steps somebody has to do? Algorithm complexity. Okay, you can modify, or that is the the whatever the DCG algorithm. Okay, or whatever the algorithm, signal processing algorithm, you can just modify the algorithm. Then you can complexity, the computational complexity can be changed. Okay, or you can reduce the computational complexity, automatically the arithmetic operation will be reduced. That means maybe 100 multiplication you want for a particular task. If you can able to change the algorithm, it can be done by 50. Well, it is better, you reduce the power by half. Okay, or if you not able to reduce the complexity, okay, algorithm complexity, maybe you can reduce the component, you can optimize the adder or multiplier complexity, that also give you some kind of saving. Okay, so if you any of this you can apply, then you have the direct area saving, delay saving, power saving. Okay, so approach, algorithm complexity reduction. Okay, so that is computational complexity directly it give, or that is the concurrency, the parallel processing, resource sharing, resource utilization. There are so many approaches are there. If you see that technical literature, you can find. Okay, few of the papers also, or you can refer, you can find all these. We referred all these, and very good designs we develop. So optimization of arithmetic unit, somebody target to computational complexity reduction. If somebody want, okay, computational complexity reduction. Okay, what are the approach somebody has to follow? Data flow analysis. Okay, in the first lecture or session, Professor Meher told about the how to derive the data flow. So you have to analyze the data flow. Okay, identify redundant computations and remove them. Okay, to remove those, you can do some algorithm reformulation. Okay, so the approach is data flow analysis, redundant computation, identify the redundant computation. Okay, and then algorithm reformulate to remove those redundant computation, so that it will give you the computational complexity reduction. Okay, reuse of arithmetic unit. Okay, that is called resource utilization. Okay, so that entirely depends how you are mapping your algorithm into the architecture. That talk about the reuse of arithmetic unit, and that exactly the architectural design basically. Okay, so that is the better your architectural design, okay, or more efficient, you can, the resource utilization is higher. Okay, so it is always expected if you are a hardware design, then resource utilization should be 100%. Okay, so that always, if your resource you are not utilizing 100%, that means your architecture is not good. Arithmetic strength reduction. Okay, in the second session, the professor talked about the arithmetic strength reduction. Even in the first session also, there is some low complexity design. Okay, some approach, a multiple common multiplication approach. Okay, that is particularly multiplier less, distributed arithmetic or codic. Okay, logic sharing and optimization, all these things you can apply. Okay, so arithmetic strength reduction. So in this hierarchy, you can see in the left side hierarchy, if the top one you can apply, you have a higher amount of saving. In the bottom one, it will be the marginal one. So the hierarchy will be based on the top to bottom, the amount of saving is higher, okay, when you move in the higher side. Okay, the delay means critical path into computational time, that is we call as a delay. How someone do the optimization? Okay, this is I understand the last slide. Reduction of time, computational time. Okay, so that one, that is the, if you remove the algorithm redundancy, okay, so that is redundant computation you can eliminate, okay, then your algorithm become more faster. Okay, so that means the computational time, you can reduce the computational time. Or because that you know, most of the algorithms are optimized, you know, there is very limited scope to change the algorithm. Okay, or reduction of critical path delay. Okay, you can reduce the critical, within a critical path, generally the gates, okay, so combinational components are there, so you can reduce the number of gates in the critical path, your critical path becomes shorter. Okay, so that exactly require the logic optimization. Okay, so logic optimization, through logic optimization you can reduce the number of gates in the critical path. Okay, or if that is not possible to optimize a logic, because already the logic is optimized, then the simple way is the pipelining. You can break the critical path by inserting a flip-flop. Okay, so that is called the pipelining. But pipelining should not be the first approach, it should be the second approach, because pipelining, if you insert the pipelining, okay, you have to apply a flip-flop, and flip-flop consume the energy. So that means some overhead you are adding into a design. Okay, more pipelining you can apply, more deep flop or registers or deep flip-flop into a design, that means your design obviously going to increase your power consumption. So that should not be the first approach. Logic operation should be first, then you can follow the pipelining. So in summary, what should be the design strategy? In a very 2-3 points. Okay, if your objective is area, deal and power optimization, okay, so that is the design constraint generally. So different algorithms have different computational memory complexity. Okay, so in general, all algorithms, one approach cannot fit into everyone. Okay, because different algorithms have their different computational memory complexity. Computational complexity also vary with throughput rate or choice of architectural design. Computational complexity also vary with throughput requirement. That means the how many output you want per second. If you more output, then you have a more your computation will have to perform. Okay, so that is the choice of architecture design. Your architecture could be serial, semi-parallel, full parallel, anything. It depends how much speed or throughput you want. So accordingly, you have to provide perform those amount of computation. Okay, or that amount of computation. So design strategy, selection of the architecture design. First, either you see how much the throughput you want, then you choose the serial or semi-parallel or full parallel, which type of design you want. Okay, then selection of design approach and prioritize. Design approach means which optimization you want to apply, memory optimization first, or arithmetic optimization first followed by the memory, or delay optimization first followed by the arithmetic or followed by the memory. So that you have to prioritize. Okay, and that it will help you if you exactly estimate the complexity, you project all the each of the block, how much the resource sharing, okay, all everything. Okay, so that it will help you to figure out, okay, which one you target first. Memory optimization, if you target, because if your design is going to consume 85% of memory, then it is better to target the memory first, okay, than the arithmetic. Note that one you optimize, other will be become, there is some overhead in the other component. Okay, so that's why what meant, maybe if you optimize 85%, if you optimize, maybe you can add 1% in the arithmetic. It is not going to affect much, but that saving will be give you a lot of amount of saving in terms of power up energy. So that strategy somebody has to find out, keeping depending on the type of algorithm the person is dealing or what type of application it at hand, everything. Thank you. I hope I am little overstressed, extended the time I extended, and sorry.
It's okay, sir. No
An-
problem.
any questions in a quick 10 5
Now
5
now
minutes
the
or 10
forum
minutes?
is open to ask the question, so, sir. I would like to request all the participants to ask the questions, please.
Sir, I would like to ask, sir, you have given the paradigms for algorithm design. So my question is, sir, so the paradigms that you have mentioned over here just before a few slides, whether that's paradigms are same for online algorithms, sir?
Online algorithm means?
For real time purpose, these days like all IoTs are working on the real time purpose on or real time softwares they are seeking for, like RTOS they are using real time operating system. Whether that algorithm is that algorithm, the paradigms that you have mentioned will work for that real time operating systems.
Hey, look at actually basically what happened, we are talking about the hardware accelerator. Basically hardware accelerator never use the your operating system. Okay, so they never use any operating system. It is just one instruction and it will run so it will run and give you the output. Then as such there is no operating system. So otherwise if you use a operating system, then your memory size, system memory will has to be increased manifold, and that itself it will be more power consuming. Okay, so it is free from, it is a hardware accelerator never use any operating system. It is just a single or maybe a few instruction, it will start running the algorithm, it will run and give you the output result.
For like a bigger system we are using RTOS. The if we look into the smaller system, we may be using some firmware and other softwares, but whether that is a small system or a large system, we need some software to communicate through the internet and that through the IoT. So my question is that whether that softwares and that algorithm is following the same paradigms that we have mentioned over here.
No. It is, we are talking about a complete hardware design, right? A complete hardware design, and we are discussing about how to optimize the power and the resource and power consumption, energy consumption in a hardware design. It is, there is no, that is the operation nowhere it is going to be controlled by any software, right? These are all, every component is fixed, their operation is also fixed.
Yes, sir. Yes, sir.
If you want to make it, you can do that, there is not an issue. If you do it, it will be maybe your design become more reconfigurable, where your operations can be, you can reconfigure. Okay, you can change. So then what happened, your system complexity it going to be increase. Then what happened, the power consumption accordingly it will be increase. Your hardware accelerator, what happened, it's supposed to be consume very small energy. That means in terms of millijoule is very higher, even nanojoule they consume. In order of nanojoule or a maximum you can call a millijoule they can consume. Okay, so that to achieve that that type of things, you have to make the complete, all the components are completely hardware.
So is it possible to like make a, like the real like modern days system completely hardware based? Like for example, I'm saying like if I'm having a camera, like let's say for camera for having a bouquet mode camera setting, so it can be hardware based or it can be software based. But if
Actually what happened, what you are talking, even in a you can a MacBook or a MacBook you can take, or a Apple system, or take laptop you take. There are, you can just look at the literature nowadays. Your laptops or everything, or the processing devices, they are inside that. There are 30 to 40% of all the peripheral component that become the hardware. Completely hardware accelerated. Hardware accelerator means it completely hardware. Okay, then these components are controlled by a software which is also seated in another, that is the either you have a off chip, off chip memory, you have some software will be there, it is outside the chip. If you look at, just let me show you once again. Okay, let me show you that layout once again. This one. Okay, the off chip memory, you can just look at the off chip memory. Maybe your software or whatever you are calling the outside world something, it is controlled by some software, then that might be in the outside of the chip, that is called off chip memory. Okay, but actually we are more concerned about this core. This core is basically the hardware. Okay, and it is just takes few instructions or the few required data from the off chip memory or instruction, and it will run and deliver the output again back to the off chip, which will be sent to the outside world, to the off chip, right?
Sir, yes, sir. Thank you, sir.
Okay.
Any more questions from the participants?
Yes, hello sir, good evening.
Yeah.
Sir, I would like to know that in these approximate systems, some amount of error is tolerable, but how much error is tolerable for a particular system? Like how much percentage of error? Uh, how can we determine that this much amount of error would be okay for a particular system?
No, the error can be tolerated by the system. It is a computing device. Okay, it is just calculating. So any amount of you can introduce, it can do calculate. Okay, that is not a problem. Whatever your question is basically, how much the error application going to tolerate. Okay.
Yes, sir. Yes, sir.
So that depend on the application dependent. But for example, a video, or maybe an image. Okay, the image, you are taking you are collecting an image, and that you are processing and delivering to some recipient. Okay, or so to some user. But depending on the which type of application you are delivering the image. So if the application, it will run with a very low resolution output, then why it is such a high resolution you will send to the user? You send a very low resolution report, the image, na. So in that case, what happened? You introduce the error and reduce the resolution, and that error you can utilize to make your design lighter. So it is entirely application dependent.
So it will vary from application to application.
Yeah. Completely vary.
And sir, one more point, like what is the difference between this critical path delay and computational delay?
Yeah, right. Critical path is the, that in the first session also it is discussed. Critical path basically decides your clock rate. Okay, might be in your system, maybe your i7 system you are doing, maybe it is 2 gigahertz clock. Okay, but 2 gigahertz clocking rate might be to complete a particular task, you maybe use some 1000 clock cycles. So that called the computation time, which include 1000 clock cycles to complete a task. Because to calculate output, you require several clock cycle to complete a several operation. In a one clock cycle, it may not be your entire operation will complete, na. Multiple clock cycle you always you include. So that computation time is the how many clock cycle you are using, okay, to complete a particular task, or maybe to calculate one output. You given an input, because your design having so many registers or memory, so many memory operations, and every memory operation you have to spend one clock cycle. Okay, so like that, how many clock cycle you are spending to calculate your output. Let my path from input to output, I am spending, let it be 10 clock cycles, and my clock cycle is, let it be 1 microsecond. Okay, so I required my 10 microsecond, my computation time going to be 10 microsecond, like that. Is that clear?
Yes. Yes, sir. Yes, sir. Yes, sir. Thank you, sir.
Any more questions from the participants? Okay, sir. No more question, and we have received some very good gratitudes for you, sir, in the message box. And during the session, we have 69 participants we have seen in the chat box. And thank you, sir, for the discussing on the very good topic on the approximate computation strategy for energy efficient hardware design for signal processing algorithm. Sir, you have nicely explained the fundamentals, needs, and the challenges, scopes of the approximation computation. That the ideas you discussed in approximation technique will definitely help the participants in their research work. Specifically, the discussion of challenges in the hardware design will ignite us to develop new ideas. The information you said on the strategy of optimization hardware design, memory power consumption will definitely helpful for our participants. Will definitely follow the work you suggested. Thank you, sir, for the beautiful talk you presented.
Thank you. Thank you all. Prandu, Pranav.
Okay, thank you, sir. Good night, sir.
Good,
And good
night.
night to all the participants. We will conclude the session here.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.